Okay, hello student, good day. My name is Oelami Janet and welcome to chemistry class. The topic of our class for today is water. Okay, before I go ahead, I would like to tell you to assume a very conducive sitting position that is devoid of noise and distraction. And you also have to get your writing materials with you so we can have the class as interactive as possible. Thank you. So to our introduction, life depends on water. Water is used all over the world in large quantities for drinking purposes, cooking, dyeing, washing, raising steam to drive engines or turbines, which are used in electricity generation, and also as a solvent in industrial processes and a lot more. Okay, water rarely occurs in pure form in nature. That means you rarely find a pure water in its natural state. So over to our objectives. These are the things we have to achieve at the end of this class. Number one, we have to know the meaning of water. We know the structure as well as the bond as well as the shape. So then we move over to sources. There are two major categories of water. Underneath we have different examples. Okay, then we move to treatment of municipal water. Okay, where you treat water for the whole township supply. Then we move to the final one, which is hardness of water. And we have to look at the types of hardness and removal of hardness. So what is water? Water is an example of molecular substance. A molecular substance is a substance that is usually liquid at room temperature. That means it's usually liquid at room temperature. It has less than 300 degrees Celsius. Okay, Celsius is a metric grade that is being used in place of centigrade. So it is also regarded as an oxide of hydrogen. That means is addition of oxygen to hydrogen, which you can see in chemical equation down here. As 2 mole of hydrogen gas reacting with 1 mole of oxygen gas to give 2 molecules of water. So here we say water is most abundant, okay, both in plant and animal tissue. You can see water making up more than 70% in growing plants, and 70% of water make up human tissues also. So moving to structure of water, here we have oxygen being the central atom, having valence electron of 6. That means we have 2 lone pairs. These are the 2 lone pairs of electron, and we have unpaired electron also to make it 6 unpaired, 2 unpaired electron for oxygen. So hydrogen comes in and bond with one of this and also bond with one of this to make the molecule to achieve an octet configuration, which is very stable. So you can see something like this dipole negative and dipole positive. That means they behave as an ionic compound, although the chemical bonding between the hydrogen and oxygen is called hydrogen bond, but they do so because they are polar solvents. If you look at the second one, which is B, the structure of a polar water molecule, where you have the hydrogen atom, which is the nucleus of hydrogen, bonding to another oxygen atom of another water molecule. That's how they keep on bonding and bonding to form a bigger molecule. You can see it all there. And also in the structure of water molecule, it has approximately 105 degrees due to the repulsion of this lone pair. There's a repulsion which brought up the shape of the water molecule to be a bent or an angular shape. Okay, so when we talk of solid water, which is ice, we talk of their spatial arrangements. That's an arrangement in space where we have HOH. That's two hydrogen reacting with oxygen. This is the main water molecule, and this main water molecule is bonded to another molecule of water through the nucleus of hydrogen to the nucleus of oxygen in another water molecule. So the bond distance between hydrogen here and this dotted line, which is showing you there is a intermolecular length. That's intermolecular length between the hydrogen of one molecule of water to oxygen of another molecule of water. We all know that there's always attraction between positive charge and negative charge. This is what happened here. So the intermolecular distance there is 0.177 Newton meter, nanometer rather. So when you look at in between the molecule, one molecule of water, you have you can call it intramolecular bond, or you call it interatomic bond. That's 0.039 nanometer. So as you can see, the three things you have to take away from this structure is that water molecule is formed by hydrogen bond. That's the chemical bonding between the atoms that come together to form water molecule, and they assume an angle of 105 degrees. And also, there is polarity in water molecule. That means the one molecule can keep on bonding to another until they form giant molecule due to partial positive and negative charge they have. Okay, you can see for hydrogen partial positive charge and for oxygen partial negative charge. Okay, and the last one you have to take out from this structure is that they are tetrahedral shape. There's the shape in space. Okay, sources of water. We talk about two main categories under sources of water, which is natural water as well as treated water. Under natural water, we have various examples. For the first example, which is rainwater, we talk about rainwater is the purest form of water as far as I know, and is formed by condensation of water molecule in the atmosphere. The second one, which is spring water, is made up of considerable amounts of mineral salts in there. Then you also have suspended particles just like dust and bacteria. And for well water, we have it contains clay and some mineral salts also. But if you want to use, this is a good source of water, this is a good source of water, and this, if you want to use it as source of water, you have to go by two conditions. The first one is that you have to site it away from underground source of pollution such as pit latrine, and the second one is that you have to line the inside and have it covered. Okay, the other ones, which is lake, sea, and ocean water, the three of them they contain large amounts of dissolved air, mineral salts, bacteria, as well as organic remain. So before you can use this as a source of drinking water, you have to specially purify those waters. Okay, so we move to treated water. Treated water are usually prepared for the special purposes. Okay, example under treated water, the first one is distilled water. Distilled water is chemically pure water. That means it's a pure water that is made by chemical, as well as pipe-borne water, which I'm going to go into shortly. And also chlorinated water is all about the water we use in our swimming pool, the water we use in our swimming pool, which actually prevents disease and all other stuff. Chlorine is being added to disinfect the water. Okay, so that will move me to the next slide, which is treatment and supply of municipal water. Okay, so the first thing you have to do is to get your water from any source. It could be from rain, it could be from lake or sea. So the first step in purifying or treating this water is that you maintain aeration. Aeration involves exposure of the water in order for the odor and volatile chemicals to be removed. So when you expose it to air, the odor will be removed, as well as the volatile chemicals, which are hydrogen sulfide, carbon dioxide. Then the second step is coagulation. Coagulation means you have to add some chemicals like potash alum. Potash alum is aluminium potassium tetraisosulfate 6. Okay, and either you had this or you had the other one, which is sodium aluminate 3. That's NaAlO2. Okay, these two, either of the two, normally cause coagulation, or you call it flocculation. And what really happens there is that the impurity clumps together to form a big particle of dirt or float. So this one can now be easily settled. When it's settled, you call it sedimentation, where the dirt and flux settles down rapidly. Then the next step is that you pass it through filter bed where filtration is being done. Okay, pass it through filter bed to remove the remaining fine particles of dirt. Afterwards, you move it to the next step, which you are going to do disinfection by adding chemicals like chlorine to kill the germs, and you can as well add calculated amount or correct amount of fluorine and iodine in order to prevent tooth decay as well as goiter. We all know that fluorine is good in preventing tooth decay, while iodine is good in preventing goiter. So the last stage of this treatment and purification is storage. We have to store this. So after the disinfection of this old water, our water is free. That means it's clean, it's germ free, and we can now store in reservoir and distribute it to town via underground pipes. So that last stage is called the storage, where you store it in reservoir where it's being so this is the diagram right here. From source of water supply, it could be from rain or any other thing. You put it in you put the untreated water in a tank where you can easily expose it, so it can be the whole smell and volatile chemicals can be aerated. Okay, followed by flocculation, or what we call coagulation, where you had the potassium. So you follow the step, you see from there, followed by sedimentation. There is move through filter bed where it's filter, and followed by disinfection where chemical like chlorine is being added to kill the germs. And you can also add correct amounts of fluorine and iodine to prevent food decay as well as goiter. Then you store it and distribute it to the town and nearby places. So I want you to try to pause this video and do what I just did, all the 6 steps in here. I want you to write it, okay? At least you can still remember our first step involves aeration. You have to aerate to get the smell out and the volatile compounds like H2S, which is hydrogen sulfide, and carbon dioxide, then followed by flocculation or coagulation. Same thing where you can make the impurities to clumps together so it can be filtered off. So that is where they settle rapidly and you can pass through the filter bed. Okay, that's the fourth one, filter bed, to remove the fine impurities, and followed by this infection where you had your chlorine, and the last one, storage, from where you now send it through pipe to the tank. So hardness of water. What does actually, to start this slide, I'll let you know that many times we are washing our clothes, we realize we use a lot of soap, and the water is not forming foam. What we mean by foam, that's lather. Okay, so here you say water that does not form lather readily with soap is described as hard water. So, and hardness of water is due to presence of this, and this. Okay, in water, when you have calcium tetrahydrosulfate 6, magnesium tetrahydrosulfate 6, or you have calcium hydrogen triazocarbonate 4 in water, this is what causes hardness of water. And how is it being brought about? How does hardness come about? Okay, we can explain that when water flow on the soil having gypsum. Okay, gypsum is calcium 4.2 water. We call it calcium tetrahydrosulfate 6 dihydrate. So when the soil contains this gypsum, or it contains Caco3, which we know has limestone, which is calcium triazosulfate 4, we find out that this especially, which is gypsum, dissolves in water. Okay, and this one does not actually. So whenever soap, soap is our potassium or sodium salt of organic acid. Whenever soap is being added to this hard water, what the hard water does is that it dissolves the salt in water immediately and reacts with soap. So the dissolved salt in the hard water, dissolved salt is either the calcium salt or the magnesium salt or the calcium salt of this calcium hydrogen triazocarbonate 4. They are dissolved in water immediately and react with the soap to form insoluble calcium and magnesium ion. Let me show you here. This is what I'm talking about. The dissolved calcium or dissolved magnesium salts, it reacts with water, which is sodium octadecanoate. Okay, this soluble in water and this soluble in water, and when it reacts with this soap, that means magnesium or calcium, as the case may be, reacts with the soap to give us calcium or magnesium octadecanoate and also sodium salts. Okay, so this is the chemical formula here. We have the calcium tetrahydrosulfate 6 reacting with what? Reacting with octadecanoate, which is the formula for our soap right now. Okay, what happens there is that it displaces the sodium, okay, and reacts with the organic parts, so giving us this, which is scum, unpleasant scum, which is formed on your clothes when you are washing, and the other one is soluble in water. This unpleasant scum supposed to be here, so pardon me. So this one is soluble salt, which is disodium tetrahydrosulfate 6 salt. So class drill, I want you to do this for me. Why is hard water wasteful or uneconomical? Please explain. That will come up, your answer should come up in the next assignment, which I'm going to send to you. So types of hardness. We move to types of hardness. We have two major types of hardness, which is temporary hardness or permanent hardness. The first one, which is temporary hardness, is caused by presence of dissolved calcium hydrogen triazocarbonate 4, which is CaHCO3. Okay, so how can you remove it? You can remove it, one, by boiling. This symbol here is addition of it. When you add it to this compound, it breaks down to give you insoluble CaCO3, water, and carbon 4 oxide. Then the next one, which you can remove temporal hardness, is to add slaked lime. Slaked lime is our calcium hydroxide. Okay, when you add this, it gives you 2 moles of limestone, which is calcium triazocarbonate 4, and also water. This is insoluble, so it can be filtered off, then you get your good water, which is free of hardness. Okay, so we move to permanent hardness, but note, you have to know that when you're adding your slaked lime, you have to do so in correct proportion, as in you have to measure it. If you have too much of it, it becomes permanent hard water. That means it will make the water permanently hard. Okay, so permanent hardness of water. What's the cause of permanent hardness of water? It's caused by presence of calcium ion and magnesium ion in form of soluble tetraoxosulfate 6 or chloride. That means you can have it as calcium tetraoxosulfate 6, or you can have it as calcium chloride, or you can as well have it as magnesium tetraoxosulfate 6 or magnesium chloride. And they are mainly removed by using chemicals. The first one is uneconomical, so it's not being used so often, which is distillation, where you distill the water and you have your ion remaining there. And the second one is adding washing soda. This washing soda, disodium carbonate. When you add it to it, you have your soluble and insoluble. When this one reacts with this, it gives you the what? Insoluble calcium carbonate, which causes the hard water, and you can filter off, so you have your water perfect. Same thing here too. Addition of you can use it either way. You add the washing soda to magnesium sulfate, or you add it to calcium sulfate. Then the third method is that you can use caustic soda. Caustic soda is sodium hydroxide. Adding it to your water, you have this, and this is insoluble, where you can filter it off. Then the second one is also when you use magnesium tetraoxosulfate 6. So you can always follow that part. So the last but not the least is called permutate method. This is an ion exchange resin, okay, used in softening large scale water. When you have so much water you want to remove the hardness, you use this method. So this method, this is the diagram right here. So the ion exchange resin is all about permutate. So permutate is the same thing as zeolite, which is sodium. The P stands for aluminium silicate hydrate. It's an hydrated compound. So definitely if it reacts with the calcium tetraoxosulfate 6 in hard water, it gives you this, which is insoluble, which can be filtered out. And you can regenerate this method by adding sodium chloride. Then you get your soft water out, and your impurity or your insoluble compound can always be filtered off. Hope you enjoy the class. Stay tuned and be blessed. So, all about the advantages of water, you can always find them here. You have the advantages and disadvantages. It's quite explanatory for you to read and understand. Thank you all.